Hello everyone, this is Shumon here and you are watching my channel Learning Chemistry. In our previous video, we learned about oxidation state, oxidation number and how to calculate the oxidation number of an element. Today I would like to discuss some more examples of oxidation number calculation with some exceptional cases. I have uploaded 2 videos related to oxidation reduction reaction till now. Those of you who haven't seen my previous classes, please watch those videos. So students, let's begin our today's class. Students, our first compound is dichloromethane. Here we have to calculate the oxidation number of carbon. So let the oxidation number of carbon be X. So now we can write X for the carbon plus 2 into plus 1 for the 2 hydrogen atom plus 2 into minus 1 for the 2 chloride ions. So the overall oxidation number of this compound is 0. Therefore X plus 2 minus 2 equals to 0. That is X equals to 0. So here the oxidation number of carbon present in this dichloromethane compound is 0. Our next compound is potassium manganate, that is K2MnO4. Here we have to calculate the oxidation number of manganese. Let the oxidation number of manganese be X. So we can write 2 into plus 1 for the 2 potassium atom plus X for this manganese atom plus 4 into minus 2 for the 4 oxygen atom present here, and the overall oxidation number is 0, or 2 plus X minus 8 equals to 0. Therefore X equals to 8 minus 2 equals to plus 6. So the oxidation number of manganese present in the potassium manganate compound is plus 6. Our next compound is nitrosonium perchlorate. Here we have to calculate the oxidation number of chlorine atom. So let the oxidation number of chlorine atom be X. And here we have to know that in this compound NoClO4 exists as NO plus and ClO4 minus. Okay. So let's calculate it. Plus 1 for this nitrosonium ion plus X for the chlorine atom plus 4 into minus 2 for the 4 oxygen atoms, and we know that the overall oxidation number of this compound is 0, or 1 plus X minus 8 equals to 0. Therefore X equals to 8 minus 1 equals to plus 7. So here in this given compound the oxidation number of chlorine atom is plus 7. Our next example is hydrazoic acid, that is N3H, and here we have to calculate the oxidation number of nitrogen atom. Let the oxidation of nitrogen atom be X. So here we can write 3X for 3 nitrogen atom plus 1 for this hydrogen atom, and the overall oxidation number of this compound is 0. Therefore 3X equals to minus 1, or X equals to minus 1 by 3. So the oxidation number of nitrogen present in this hydrazoic acid molecule is minus 1/3. The next example is pyrosulfuric acid, which is known as oleum. Here we have to calculate the oxidation number of sulfur. Let the oxidation number be X. So 2 into plus 1 for this 2 hydrogen atom plus 2 into X for this 2 sulfur atom plus 7 into minus 2 for this 7 oxygen atoms, and the overall oxidation number is 0, or 2 plus 2X minus 14 equals to 0, or 2X equals to 14 minus 2 equals to 12. Therefore X equals to 12 by 2. that is plus 6. So the oxidation number of sulfur present in this pyrosulfuric acid compound or oleum is plus 6. Our next example is sodium nitroprusside molecule, and here we have to calculate the oxidation number of iron atom. Let the oxidation number of iron be X. So let's start. 2 into plus 1 for this 2 sodium atom present here, plus X for this iron atom, plus 5 into minus 1 for this 5 cyanide ions, plus 1 for this nitrosonium ion, and the overall oxidation number is 0, or 2 plus X minus 5 plus 1 equals to 0. Therefore X equals to 5 minus 2 minus 1 equals to plus 2. So the oxidation number of iron present in this sodium nitroprusside molecule is plus 2. Next, this is a very well known compound. It is brown ring compound, and here we have to calculate the oxidation number of iron. Let the oxidation number be X. So here X for this iron atom, plus 5 into 0 for this H2 molecule as it is a neutral ligand, plus 1 for this nitrosonium ion, plus minus 2 for this sulfate ion, and the overall oxidation number is 0, or X plus 0 plus 1 minus 2 equals to 0. Therefore X equals to plus 1. So here in this brown ring compound, the oxidation number of iron is plus 1. Clear? Next, this is hypophosphorus acid, and here we have to calculate the oxidation number of phosphorus. Let the oxidation number be X. So here 3 into plus 1 for this 3 hydrogen atom, plus X for this phosphorus atom, and plus 2 into minus 2 for the given 2 oxygen atoms, and the overall oxidation number is 0. Therefore 3 plus X minus 4 equals to 0. So X equals to plus 1. The oxidation number of phosphorus present in this hypophosphorus acid is plus 1. Next, this is sodium dihydrogen phosphate molecule, and here we have to calculate the oxidation number of phosphorus. Let's plus 1 for this sodium atom, plus 2 into plus 1 for these 2 hydrogen atoms, plus X for this phosphorus, plus 4 into minus 2 for these 4 oxygen atoms, and the overall oxidation number is 0, or 1 plus 2 plus X minus 8 equals to 0. Therefore X equals to 8 minus 2 minus 1, that is plus 5. So the oxidation number of phosphorus present in this sodium dihydrogen phosphate molecule is plus 5. Next, this is sodium hydrogen sulfate or sodium bisulfate molecule. Here we have to calculate the oxidation number of sulfur. Let's start. Plus 1 for this sodium atom, again a plus 1 for this hydrogen atom, plus X for this sulfur, and plus 4 into minus 2 for these 4 oxygen atoms, and the overall oxidation number is 0. Therefore 2 plus X minus 8 equals to 0. So X equals to plus 6. Here the oxidation number of sulfur present in this sodium hydrogen sulfate or sodium bisulfate molecule is plus 6. Our next example is sodium borohydride. We all know that this is used as a reducing agent, and here we have to calculate the oxidation number of boron atom. Let's start. +1 for this sodium atom, plus X for this boron atom, plus 4 into -1 for this hydrogen atom. Why I take -1 here? Because in this compound, what is the name of this compound? This is sodium borohydride. That is, hydrogen is present as hydride here. In our previous video, we learned about that where the hydrogen atom present as hydride, we have to take the oxidation number of hydrogen atom as -1. That's why we take -1 for this 4 hydrogen atom here. And the overall oxidation number is 0. Therefore, 1 plus X minus 4 equals to 0, or X equals to 4 minus 1 equals to +3. So the oxidation number of boron atom present in this sodium borohydride molecule is +3. Clear, everyone? Our next example is calcium peroxide, and here we have to calculate the oxidation number of oxygen atom. First of all, we have to take +2 for this calcium atom, because calcium atom is present in alkaline earth metal group, that is in group 2A. Next, +2 into X for these 2 oxygen atoms, and the overall oxidation number is 0. Therefore, 2X equals to -2 and X equals to -1. I hope you remember that I told that the name of this compound is calcium peroxide, and we know that in any peroxide compound the oxidation number of oxygen atom is always -1. Clear? Next, this is sodium tetrathionate, and here we have to calculate the oxidation number of sulfur atom. Let the oxidation number of sulfur atom be X. So here 2 into +1 for this 2 sodium atom, plus 4 into X for these 4 sulfur atoms, plus 6 into -2 for the 6 oxygen atoms, and the overall oxidation number is 0. Or 2 plus 4X minus 12 equals to 0, or 4X equals to 12 minus 2, that is 10. Therefore, X equals to 10 by 4, that is plus 2.5. Clear? This is ferroferric oxide, and here we have to calculate the oxidation number of iron atom. Let the oxidation number of this iron atom is X, so 3 into X for this 3 iron atom, plus 4 into -2 for these 4 oxygen atoms, and the overall oxidation number is 0. Or 3X minus 8 equals to 0, therefore X equals to plus 8 by 3. Clear? Since electrons cannot be transferred fractionally, the fractional oxidation state of an element seems to be a hypothetical case. But in compounds like Fe3O4, Na2SO4O6, the oxidation states of iron is here plus 8 by 3, and the oxidation number of sulfur is plus 2.5 respectively. In fact, fractional oxidation state is only the average oxidation state of an element when 2 or more of its atoms with different oxidation states are present in a compound. For such compounds, the actual oxidation state can be determined by knowing the structure of that compound. Again, we are going to calculate the oxidation number of sulfur atom present in this compound by knowing its structure. The structure of this compound is NaO S again an ONA, and 4 oxygen atom is coordinatively binded here with these sulfur atoms. In this molecule, the oxidation number of 2 sulfur atoms that are covalently linked is 0. If the oxidation number of these 2 remaining sulfur atoms be X, then 2 into X for this remaining 2 sulfur atoms plus 2 into 0 for this sulfur-sulfur covalently linked up bond S plus 1, 2, 3, 4, 5, 6. 6 into minus 2 for this 6 oxygen atoms plus 2 into plus 1 for these sodium atoms, and the overall oxidation number of this compound is 0. So 2x minus 12 plus 2 equals to 0, or 2x equals to 12 minus 2 equals to 10. Therefore x equals to 10 by 2, that is plus 5. So the oxidation number of sulfur present in this molecule is 5. Next, Fe3O4, ferroferric oxide. Ferroferric oxide is a mixed oxide having the composition of FeO dot Fe2O3, that is ferrous oxide and ferric oxide. So in this part, in ferrous oxide, iron is present as Fe2 plus state, that is here the oxidation number of iron is plus 2, and in this part, in case of ferric oxide, here the oxidation state of iron is Fe plus 3, that is the oxidation number of iron is plus 3. So here we are having two oxidation state, that is two oxidation number of iron atom, that is plus 2 and plus 3. Next, this is chromium peroxide or chromium oxide peroxide. According to the usual method, the oxidation number of chromium in this CrO5 molecule would be plus 10. If you consider the oxidation number of chromium be X and 5 into minus 2 for these 5 oxygen atoms, and the overall oxidation number is 0. Therefore, X equals to plus 10. Clear? However, the oxidation number of chromium can never exceed 6 because total number of electron in its 3d and 4s orbitals is 6, as the electronic configuration is of chromium is argon 3d5 4s1. So from this electronic configuration we can easily say that the oxidation number of chromium can never exceed 6. Now we have to think about the structure of this compound. The structure of the given compound is let the oxidation number of chromium be X. So we can write X for this chromium atom plus 1 into minus 2 for this oxygen atom, and plus 4 into minus 1 for these 4 oxygen atoms linked in O bond O. 4 oxygen atoms linked in O bond O, because this is peroxide bond, and the overall oxidation number is 0, or X minus 2 minus 4 equals to 6. Therefore X equals to plus 6. This is the oxidation number of chromium present in this chromium oxide peroxide or chromium peroxide, that is CrO5 molecule. Our next example is sodium thiosulfate molecule, and here we have to calculate the oxidation number of sulfur atom. Let the oxidation number of sulfur atom be X. So here we can write 2 into plus 1 for these 2 sodium atoms plus 2 into X for these 2 sulfur atoms plus 3 into minus 2 for these 3 oxygen atoms, and the overall oxidation number is 0. Therefore 2 plus 2x minus 6 equals to 0, or 2x equals to 6 minus 2 equals to 4. that is x equals to plus 2. So according to the usual method, the average value of oxidation number of sulfur in sodium thiosulfate molecule is plus 2. Now we have to think about its structure. The structure of this molecule is however, in the reaction of sodium thiosulfate with dilute H2SO4, one of the two sulfur atoms in sodium thiosulfate is precipitated as sulfur and the other is oxidized to sulfur dioxide. Therefore, the two sulfur atoms in this sodium thiosulfate molecule are not identical in nature. Consequently, their oxidation numbers cannot be the same. The chemical structure of sodium thiosulfate molecule indicates that the two sulfur atoms in it are linked by a coordinate bond. The oxidation number of sulfur accepting the electron pair in this coordinate bond is considered to have an oxidation number of -2. If the oxidation number of the other sulfur atom is taken as x, then we can write 2 into plus 1 for these two sodium atom plus 3 into -2 for these three oxygen atoms plus x for these sulfur atoms plus 1 into -2 for this sulfur atom which holds by coordinate bond. Okay, so let's 2 minus 6 plus x minus 2 equals to 0. Sorry, I missed it. This is equals to 0. Therefore x equals to this 2 minus 2 gone and x equals to plus 6. So the oxidation number of sulfur atom present in this sodium thiosulfate molecule is plus 6. Next, this is H2SO5, that is peroxomonosulfuric acid or known as Carr's acid. Here, according to the usual method, the oxidation number of sulfur atom in this Carr's acid molecule is plus 8. Let's do it. 2 into plus 1 for this 2 hydrogen atom plus x for the sulfur atom plus 5 into -2 for these 5 oxygen atoms. Therefore, it is 0, or 2 plus x minus 10 equals to 0, that is x equals to plus 8. But the oxidation number of sulfur can never exceed plus 6. Here we have to think about its structure. The structure of this compound is HOSO OH and here double bonded O. Let the oxidation number of sulfur atom be x. So we can write x for this sulfur atom plus 2 into 1 for these 2 hydrogen atoms plus 2 into -1 for these 2 oxygen atoms held by O bond O, that is by peroxide bond. For oxygen atoms held by O bond O, okay, plus 3 into -2 for this remaining 3 oxygen atoms, and the overall oxidation number is 0, or x plus 2 minus 2 minus 6 equals to 0. These are cancelled out, therefore x equals to plus 6. So the oxidation number of sulfur atom present in this Carr's acid or peroxomonosulfuric acid molecule is plus 6. Next, this is potassium triiodide molecule. In the structure of this molecule, we have K plus I bond I, a coordinated bond with another I, and the overall charge of the sphere is -1. Okay. in Ki3, the I minus ion forms a coordinated bond with this I2. So the oxidation number of each iodine atom in this I2 molecule is 0, and the oxidation number of K plus is plus 1. Therefore, the oxidation number of another iodine is minus 1. That is plus 1 plus 0 for this iodine molecule and plus X, and the overall oxidation number is 0. Therefore, X equals to minus 1. Okay. So, from this calculation, we get that here two types of iodine is present. Two iodine is participating to making a bond in iodine molecule, that is I2. So the oxidation number of iodine is 0, and in the another I, this is present as I minus, its oxidation number is minus 1. Clear? Our next example is H2H2O8, that is peroxo disulfuric acid, or this is known as Marshall's acid, and here we have to calculate the oxidation number of sulfur atom present in this molecule. According to the usual method, we have to calculate the oxidation number of this sulfur atom. 2 into plus 1 for these two hydrogen atoms, plus 2 into X for these two sulfur atoms, plus 8 into minus 2 for these 8 oxygen atoms, and the overall oxidation number is 0, or 2 plus 2x minus 16 equals to 0, or 2x equals to 16 minus 2, that is 14. Therefore, x equals to plus 7. But we know that the oxidation number of sulfur atom never exceeds plus 6. Clear? So we have to think about its original structure. The structure of this compound is HOSOOS, and there is a double bond of oxygen present in this sulfur atom. Clear? Let the oxidation number of sulfur be X. So we have to write 2 into X for these two sulfur atoms, plus 2 into plus 1 for these two hydrogen atoms, plus 6 into minus 2 for these 6 oxygen atoms, that is 1, 2, 3, 4, 5, 6, and finally 2 into minus 1 for these 2 oxygen atoms which are linked by O bond O, that is peroxide bond. For oxygen atoms holds O bond O. Okay, and the overall oxidation number is 0, or 2x plus 2 minus 12 minus 2 equals to 0. 2 minus 2 cancel out. 2x equals to 12. Therefore, x equals to plus 6. So the oxidation number of sulfur atom present in this Marshall acid or peroxo disulfuric acid is plus 6. Clear? So students, that's all for today. Hope you understand everything about the calculation of oxidation number in this type of exceptional cases. In our next class, we will discuss about oxidation reduction in terms of oxidation number, identification of oxidant and reductant on the basis of oxidation number, auto-oxidation reduction, and disproportionation and comproportionation reaction. Thanks for watching my class. If you have any doubts or suggestions, please tell me in the comment section. Those who are not subscribed my channel till now, please subscribe it and press the bell icon to get regular updates of my new videos. And don't forget to share it with your friends. See you in the next class. Take care, stay home, stay safe.